Here we have two functions, f of x, which is equal to 2x, g of x, which is equal to 3x squared plus 1. And remember what that means. F of x being equal to 2x means we find ordered pairs, we find values for the function by taking some value for x, placing it here where x is in the expression, performing the arithmetic, and that's how we get the function's value. And remember, the function's value in terms of our coordinate plane, in terms of graphing, the function's value is equivalent to the y value. So we have these two functions, and we've worked with functions. We've evaluated functions. Let's say we wanted to evaluate the function f at x being 3. So that means wherever there was an x, we replace it with a 3. In fact, that's what this symbolism tells us. It says, whatever you put here, put in place of x in order to perform the evaluation. So f at 3, the function's value at 3 would be 6. Or we could find g of 2. And we would replace in the expression for g, we would replace the x with 2. So 2 squared, do the exponent first. 2 squared is 4. 3 times 4 is 12. 12 plus 1 is 13. So g at 2 is equal to 13. The function value for this particular function is 13 when x is given the value of 2. So the ordered pair that we would create here for the function f would be the ordered pair 3, 6. The ordered pair that we've created here for the function g would be the ordered pair 2, 13. And that's how we could get some ordered pairs if we wanted to sketch the graphs of those functions. Of course, we know this is a linear function. Its graph is always going to be a straight line. This is a quadratic function. Its graph is going to be a parabola. And in particular, since the coefficient of the squared term is positive, it would be a parabola that opens up. It's still on the y-axis. It would be shifted up 1, but it's still going to be symmetric with respect to the y-axis because there's no first power x to shift it left or right. So we've evaluated functions like this before. And we've even done wild and crazy evaluations like this. We've evaluated a function like f at x minus 2, which again, remember what this notation tells us. Whatever you put here in the parentheses, you put that in place of x in the function and simplify the expression as much as you can. So wherever there was an x, I replaced it with x minus 2. And then I simplify the expression. In this case, multiply through to remove the parentheses. 2x minus 4. So f, the function f evaluated at x minus 2, gives me the expression 2x minus 4. Well, what if we evaluated that function f at 3x squared plus 1? Then again, wherever there's an x, we're going to replace it with that entire expression, 3x squared plus 1. Which would give us 6x squared plus 2 when we multiply through and remove the parentheses. Now, does this expression, 3x squared plus 1, look familiar? Well, it should. It's the expression that defines the function g. So in actuality, this expression right here is f evaluated at the function g. Wherever there was an x in the function f, we replaced it with the entire expression that was g of x. the entire expression that defines the function g of x. When you evaluate a function at another function, you are performing what is called a composition of functions. You are composing the functions. And we have a special symbol that we use to indicate composing functions. It's this little raised circle that is smaller. It's not the normal size of an O, it's smaller, but it is hollow. It is a circle, not a dot. The dot would indicate we are multiplying the functions. The empty dot, the circle, indicates composing functions. So we have formed the composition of function f composed with function g. And the way we do that is we evaluate the function f at the expression for the function of g of x. And in this case, f composed with g would give us the function 6x squared plus 2. Well, let's see what we would get if we reversed the composition. So f composed with g of x, which is f evaluated at g of x, gave us 6x squared plus 2. Wherever there was an x in f of x, we replaced it with the entire expression that defines g of x and simplified. Now, let's look at g composed with f. So now, it's g that will be evaluated at the expression for f of x. So in this case, wherever I have an x in g of x's expression, I'm going to replace it with whatever f of x is defined as, which is 2x. So wherever there was an x here in g of x, I replaced it with the entire expression for f of x. And now I'll simplify. Well, the square of 2x is 4x squared. And now I can multiply and have 12x squared plus 1. So f composed with g gave us the function 6x squared plus 2. G composed with f gave us the function 12x squared plus 1. So this is another new operation we can perform on functions. We looked at performing other operations with functions, creating the sum function, which is where we add together the expressions, creating the product function, where we multiply the expressions to create a new function expression. So we've looked at the sum function, the difference function, the product function, the quotient function, and now this is the composition of these two functions. And just as in those other circumstances, depending upon the direction you're performing the operation, here I'm composing f with g, here I'm composing g with f, I can produce two different functions. In the next video, we'll talk about how you evaluate the composition of functions.